On to the second part of this little screencast, and this next presentation will be basics about inferential statistics. So, as we saw in the little video on descriptive statistics, really the tools we applied there had the purpose of getting some kind of idea about the basic properties or characteristics of the data that we actually collected, the sample. When we use inferential statistics, what we want to do is really to learn something about whether the observations that we have made in our sample data, the data that we have collected, is likely to generalize beyond that sample. That is, if the extent to which our sample data represents a phenomenon that is more general. Often we use experiments to test hypotheses concerning contrastive conditions. That is, rather than just collecting data from one particular task, often what we do in experiments is that we compare task performance in, let's say, two slightly different conditions to isolate the effect of that given condition. And one very kind of general kind of experimental design that we apply there is a within participant or within subject comparison. In this particular case, we have one participant that solves a task in two different conditions, or solve two slightly different tasks maybe, and we then want to test if there's any kind of difference between the task performance in one condition compared to another condition. So we might have a test condition and a control condition, or as we saw it in the eye tracking study, we have a eye contact condition and a non-eye contact condition, but the task is comparable on all our other kind of parameters. We also have an example from the experiment on the graphical science of the Pictionary game, where we could compare, for instance, the science systems that a participant involved in round 1 to the science systems that they evolved in round 2 of the game. And that would be a comparison within participant, or within, in this case, a dyad, or a pair of participants. Another kind of contrast that we often use in experiments is a between participant or between subject contrast. So we have two populations of participants that differ on some kind of crucial parameter, and we then observe the extent to which they perform differently at the same task. So we have seen examples of that in comparative studies of children and chimpanzees, but also actually again in the Pictionary game, where we had the comparison between community pairs and isolated pairs. So there we have different people solving exactly the same task, but what we want to measure here is rather kind of the effect of the fact that these people belong to different conditions. And what we use the inferential statistics is to investigate whether a difference in mean between now two different conditions or two different populations is a consistent and reliable difference that is likely to generalize beyond the observations that we have made in our local little experiment. So for that we use significant tests, and the concept of significance has to do with the assessment of whether an observed effect reflects a pattern rather than just occurs due to chance. And why is it that we need to test this kind of thing? Why is it that we need particular tools to see if there's a difference? Now, here we have a situation in which we may have collected, again, some reaction time measurements in two conditions. Let's just say for the purpose of the example that we would have we would test someone on the signs from the isolated pairs and from the community pairs. And we should think that it is enough just to look at this graph, and we can clearly see that there supposedly is a difference here. But if we kind of go back and look at some of the plots that we applied in the previous little screencast on descriptive statistics, we notice that the actual data that constitute these two means are quite dispersed. So we have quite a big variation here. So this plot relates to the first bar here. So the actual measurements that make up this mean seem to be distributed over a huge variety of collected measurements. The same goes for this second one. And what we can do now is we can actually put these on top of each other. We can superimpose them on top of each other. And what we will see here is that the two means, like this mean and this mean, that is reflected over in this graph, is actually, when we look at the raw data and how they are distributed in this plot, we can clearly see that they are not that different. Actually, is that we have a lot of overlap of variance. So we see that the variance that makes up this mean and the variance that makes up this other mean overlap to a huge extent. We can also see that it is quite probable that the amount of variance within this condition, the blue condition, is greater than the amount of variance that is between the two conditions, the blue and the red one. This is crucial. Now let's try and plot these data in a way similar to, here's the two means, similar to how we plotted them in the previous video, where we put on the error bars, and we here observe that we have really huge error bars reflecting the great amount of variance in the sample. So in this particular case, though we observe a difference here, that difference is very likely not to be statistically significant. In other words, it's pure chance that there happens to be a difference in means here, because really what we observe is that people do not really perform very differently in these two conditions. Now let's look at a different kind of situation. So here I actually already from start plotted some error bars expressing the standard deviations in a situation where we also have two conditions with the same difference in mean. So the only difference here in this case from the previous one is that we have less variance. And if we again plot the histogram here with the distributions of data, we might already here notice that it seems that the variance are now covering different parts of the space down here. So we have this one skewed a little to the right of this one, and we can again superimpose them on each other. And we now notice that there seems actually to be a real difference here between the two conditions. So we have a blue one covering a different part of space here than the red one. Also, of course, we notice that we don't have the same degree of dispersion of the data, that they are much more concentrated here, so there's not the same amount of variance. And in this case, we might infer alone from this graph that the difference in variance between these two might be greater than the difference of variance, or the variance within. So the variance between the two are different from the variance within each of the two conditions. And that is actually exactly the case. So in this particular case, if we again see this difference in mean, but with less variance within the condition, within the measurements we have taken, then the difference is actually suddenly significant. That is, it's far less likely that it happened by chance, this difference. Now let's go more into detail about what it means for something to be significant. So in order to establish whether a difference in mean is significant, we apply significance tests, and these tests, the purpose of those are to calculate how reliable an observed difference in mean are between two conditions. So what we are asking is, what is the probability that a given difference in mean is due to pure chance, that it's coincidental? And we could again reformulate it as, what is the chance that if we made new observations, if we went out and looked at, let's say, other infants and how they move their eyes about, what is the chance then that we would gain the same overall result as the one that we collected in our little sample? So this all has something to do about the reliability of the observations that we make and the likelihood that they will generalize to a greater sample. The concept of significance states that, and that's really by pure convention, that if there's a less than 5% probability that a difference between two means is due to chance, then this difference is statistically significant. Then we can actually establish that there's a difference between two conditions. So if, in other words, so if the probability that a certain observed difference between the means coming from two different experimental conditions is greater than 5%, if it's 7 or 10 or even 20%, then there's a likelihood that that observed difference is actually just there by chance, that it's just due to, for instance, high variation or to small sample in our data. One of the very commonly used significance tests that we apply and that we encounter in the experimental literature is the t-test. And the t-test exactly tests this. So it tests whether a difference in mean between two data series, for instance coming from two conditions or populations, is a reliable one. It does so by comparing the variance between conditions with the variance within condition, and that gives us a certain t-value. You might remember that in the first screencast on descriptive statistics, we actually saw a t-value from the Centure and Zebra study on infants gaze following behaviors, and that t-value was something like 2.7 as far as I remember, and that means that the variance between conditions were almost 3 times bigger than the variance within condition. And that is something that can tell us that this difference is likely to be reliable. But what a t-test also gives us, it gives us a t-value, but it also gives us a p-value. And the p-value expresses the statistical probability that this difference is due to chance. Other statistical tests that we will maybe encounter later on also gives a p-value. So generally this is a good first kind of place to go and something to search for when you read experimental literature, that is the extent to which we get a p-value that expresses the threshold of significance. And before we said that there was a 5% probability or less that that a difference in mean was due to chance, and that would tell us that something is significant. A p-value is always a value between 0 and 1, which means that if we get a p-value below 0.05, which then corresponds to the 5%, then the difference in mean is significant. That is, it's not longer likely to be due to chance. Again, this threshold of 0.05 is really just a convention, and often we would like it to be somewhat lower than 0.05 to really trust a finding. Here's a little summary. It's formulated in questions that I would like you to answer, at least to think about. And if you feel that you are not really able to answer these questions, I would suggest that you look at the videos once again so that you can kind of make up your mind on these things. So, first of all, what is the difference between descriptive and inferential statistics? What is expressed by the standard deviation? What is the standard deviation? Or what is it an index of? How does variation in a data sample impact its ability to generalize? For instance, how does it impact the significance of differences? If we imagine like conducting experiments ourselves, what could we do if we encounter great variation in a data sample? What could we do to help out our experiment in this particular situation? Is this p-value significant? What about this p-value? Is that significant? Now let's just have a little look at, again, at some excerpts from some of the literature that we've been reading. So now here is a little excerpt from the results section. Group comparison revealed that infants in the eye contact condition were more likely to follow the model's gaze. And then we get a little t here. This tells us that they made a t-test between two conditions, probably the eye contact condition and the non-eye contact condition. Then we have a value here. It reflects the degrees of freedom. I won't go very much into detail about this, but it actually tells us that there was not 18 but 19 participants in this sample. That is, the sample size was 19, and that gives us 18 degrees of freedom. We get here a t-value. The t-value tells us that the variance between the conditions were almost 3 times bigger than the variance within condition. And we get a p-value of 0.013, which you notice is below the threshold of 0.05. This means that the difference here between the eye contact condition and the non-eye contact condition is reliable, it's significant. So we actually can see that they were significantly more likely to follow the model's gaze in the eye contact condition than in the non-eye condition. And it also states here that they made more frequent looks toward the gazed object. Again, it's we have 19 participants, and we see here that we have a t-value telling us that the variance between conditions were twice as high as the variance within condition. We now notice that actually the p-value here is getting very close to the threshold. So this is maybe a more marginal significance, we would say. So the effect is not that strong. We can see that both in the t-value it was higher up here, it's a bit lower here, and this is still a significant finding because it's lower than 0.05, but it's more marginal. When we get down here, we can see that there are some very strong effects suddenly. Actually, with only 10 participants, we get p-values that are very low, suggesting that that here we have statistically quite strong or quite significant results. As I said, mentioned some time above, also other tests, not only t-tests, will give us p-values, but they would give us different kind of values here. But generally, you could orient to p-values to get an idea about how significant a particular finding is, or how significant a particular difference in mean is. This was all for inferential statistics, or at least for t-tests. There might follow later on some additional videos on other kinds of statistical tests. But this was all for now.